let me briefly introduce, and then I'll turn the time over to Kelly Osborne. He's been a long time friend and member of the community, so we appreciate him joining us today to share this presentation about accelerated RAID. He has a couple others from his team. We'll let him introduce them as well. And before I turn the time over to him, let me briefly highlight next week's session. We'll be privileged to have Dr. Rosemary Francis, the Chief Scientist for HPC at Altair. And she will be sharing with us some of the biggest changes to HPC job scheduling and resource management over the last 30 years. So we're looking forward to hearing what they have to say. And a brief highlight for the team behind the scenes here at Dell, putting this community together for you. I appreciate everybody's work. And with that, I'm going to turn the time over to Kelly, and I'll stop sharing now so that he can get his information up.
I appreciate the opportunity to come present to this fantastic community. I have actually attended both your in-person at SC22 and also SC23, and got to meet you in person back in Denver. So hopefully you didn't get sick. For me, it was a super spreader event, and I ended up with COVID for Thanksgiving. But we really appreciate the opportunity to talk about NVMe flash, what's happening in this storage market, and what some of these new technologies like SupremeRAID are, and how they work, so that you can see if it potentially could be applicable to your environment. So we're going to talk a little bit about those rapid changes in storage. And before I do, Guy Laporte, also from Dell, is on the call, and he's going to be presenting later as part of this, and also helping us with the questions. And I do have our Director of Customer Engineering, Bill Fields, and also Leander Yu, our CEO, on the call, so that they can help me out if one of you guys stump the chump here and I can't answer the question. So I want to make sure I have everything I need to take care of that. So we're going to talk about the traditional RAID bottlenecks and why it's coming to a head now. And then SupremeRAID and our technology and how we overcome that and implement it, talk a little bit about the performance numbers. And then I really want to jump into the aspects around HPC, where we have done a lot of work. And then Guy Laporte will be talking about the testing that we've been doing in his lab. So the later slides at the bottom will be part of this that we'll share, but we may or may not get to those slides. So hopefully we won't need to. So there are rapid changes, and I think it's pretty obvious that the adoption of flash in the market is increasing, and we're moving away from SAS and SATA to NVMe and direct attach NVMe. So it's much, much faster. And the estimates now are that 32% of the overall storage capacity is going to be flash by 2026. So it's growing fast. And in addition to the adoption, and the other problem that we're seeing, or advantage, if you will, is that flash storage is getting very fast, and it's getting faster, and it's also getting denser. It's getting faster, not from a NAND flash layer perspective. It's getting faster because of the interconnects are increasing. And when Graid started out, Graid technology started out, we were early working with PCIe Gen 3, and then 4 became kind of prevalent. And as you can see, for a typical SSD, we went from 3.5 gigabytes a second to 7. Now we're seeing 14 gigabyte a second drives on PCIe Gen 5. These SSDs are capable of, in most cases, using 4 PCIe lanes, which is where these numbers come from. And sometime this year, we're going to start seeing PCIe Gen 6. The other factor is new form factors. So traditionally, SSDs have been deployed in the same form factors that hard drives were, so that you had plug compatibility in slots and those kinds of things. And we're starting to break away from that, and you'll start to see these enterprise data center EDSFF form factors. E3 is one of the ones that Dell's really focused on, and what that allows you to do is increase the density of the number of devices that you can put into a server chassis, for example. as you can see below, we've gone from a 1U chassis with 10 U.2 drives to now 20 E3 short or E3 long devices, and even in the 2U chassis getting up to 44 devices. So you're putting more drives that are much faster into these dense environments. And so the critical part of this is RAID protection is becoming even more critical for this. If you have that many drives, and now we're starting to see QLC drives with capacity of up to 60 terabytes, when you have that much on a drive and it fails, you're going to have very long rebuild times potentially, and you could be very vulnerable to a second failure. So we have to have better technologies to protect against that kind of failure when you're talking about these capacities. So the challenge is that the traditional RAID that we've always used is very much a bottleneck. The fastest hardware RAID controllers have only just been released fairly recently as a PCIe Gen 4 device, which means at 16 lanes, it's only capable of delivering 32 gigabytes a second. And so the issue is, if you have a server chassis that has as many as 32 drives, you're never going to be able to get the potential performance of all of that NVMe flash in a traditional sense. So 128 lanes would be required to get the full performance out of 32 of these PCIe by 4 connections and these SSDs. If you try to connect all of those to a traditional RAID card, you can see there's a massive bottleneck. I'm going to go from 128 lanes down to 16. Think about what it's like when you go through a toll booth on a highway or a turnpike, and everybody has to slow down and get through that booth. And that's exactly what happens. And so we have, essentially customers and end users and environments where a very large number of very expensive drives are being purchased, but you're not getting anywhere close to the utilization of the performance that you thought you were going to get because of this bottleneck. In essence, a controller like this now is pretty much maxed out at 2 to 4 NVMe drives. If you plug NVMe PCIe Gen 5 drives into a card like this, essentially 2 of those drives will overrun that card, and it won't scale anymore. So you either have to have a lot more of these cards in your server, and that's also a slot limitation problem, or you have to come up with another way. So the way that we've traditionally gone around this is use SupremeRAID on the CPU. So Linux MD is an example of that. The big issue with that is that SupremeRAID runs alongside your applications, and it actually takes CPU cycles to do things like the parity calculations for RAID 5 and RAID 6. And so what you run into is not necessarily as much of a lane problem as you do a CPU problem, where the RAID itself can start to, the RAID infrastructure itself can start to consume 30 to 40% of a CPU, and on rebuilds as much as 75%. And as the number and speed of NVMe drives increase, the more interrupts and cycles and are required to keep up with all of this storage management. And so it itself is also a scaling bottleneck. So great technology, and our founders and very smart engineers thought of an interesting way to deploy RAID with a new approach that does 2 things. It offloads all of this processing from your CPU onto a GPU. So we're actually creating a software-defined RAID stack called SupremeRAID that we deploy on a GPU. The other thing that we developed is a patented peer-to-peer DMA technology so that the data does not flow through our card. We actually allow the data to go straight from the drives to the applications in the server. And so we'll show you how we do that. The cool thing is we're using an off-the-shelf NVIDIA GPU, and our application or driver is actually a CUDA-based application. And because these GPUs have the capability of doing mathematical calculations much more quickly than your CPUs can, they're ideal for doing these Reed-Solomon algorithms to do RAID parity calculation for RAID 5 and 6, etc. But at the same time, there's no place to plug your drives into this GPU. in this type of an environment, these drives are going to be plugged directly into the PCIe or directly into the motherboard. And we can see all of them using our peer-to-peer DMA. And this allows us to deliver 100% of that read performance to your applications. On the right side, we have some intelligent parity technology, reduction technology that allows us to deliver about 85% of the theoretical RAID 0 write performance of those drives. And so we're able to give you much faster performance in terms of RAID data protection and much faster performance in terms of read. So you're getting RAID 0 like read performance without the overhead. So we're going to go into a little bit about how this works. I've got a few slides that talk about how we implement this here. So in a traditional server, you're going to have your SSDs plugged in, your NVMe drives are plugged right in the front. So these could be U.2s, they could be EDSFF, they could be M.2s. We drop our NVIDIA GPU onto that motherboard into a PCIe slot, and then we load our driver on that, and that is what we call SupremeRAID. And it's a CUDA-based driver that's loaded onto the GPU after the OS is booted. Once we are running on this GPU, your operating system now sees a RAID controller, not a graphics card. So we change the personality of that card with our driver. We're able to then see all of the drives that are plugged in, and we can support right now up to 32 in a single server. And we can organize that into as many as 8 disk groups. Each disk group could have its own RAID level. 1, 5, 6, 10 today. We are working on some additional technologies for the future. And then out of each disk group, we can present up to 1,024 virtual disks or volumes. These are what your applications and operating system sees. And then as they read and write to it, we handle all of the work of doing the parity calculations, but we also redirect writes and reads to the drives to allow the data to flow straight to the devices, to your application, and eliminating any kind of a slot tax bottleneck here. So we've got some technical slides that I can show later if you have any questions about how that works. So we have an HA capability, and this is interesting because as Guy's going to talk about, we actually built some servers in his lab, or he did, with 2 of our cards in each server to do some BGFS testing, and he's actually done some tests with what happens if we disable a card, etc. So he'll be talking about that. But essentially, by having 2 cards in a machine, we can give you the ability to have auto failover in HA. In this case, what you would typically do is have half of your drives managed by one of our GPUs and the other half managed by another, and spread the load out. In this case, each GPU would be able to handle up to 16, because in the event of a failure, the remaining GPU would take over all of the drives in the chassis. So we still have a maximum today of 32. So that's how you would organize that. But if that card failed, we would take over processing here. No loss of performance, and now you can schedule time to replace that failed card. So we do have a number of different models that we support. We've just released SR1001. The card that we use here is an NVIDIA T400. And because it's a very inexpensive GPU, it's a small form factor, half height, half length, a single wide card. And the amount of CUDA cores and DRAM on this card limits us to about 8 to 10 drives. So anything more than that in this card can't keep up. But it's very inexpensive, so it's a great product to deploy into graphic workstations, gaming desktops, single node servers doing AI/ML and those kinds of things. As you get to where you need to run a larger number of drives and need more performance, we have a solution based on the T1000, which is a bigger version of this card. It has more cores and more RAM. And we can support up to 32 drives. This is a PCIe Gen 3 card, and it's a single slot card. So it's very, very good to use in one-use servers and denser environments. We also have the SR1010, which is what Guy Laporte's been testing with. This is our flagship A2000 NVIDIA A2000 based PCIe Gen 4x16, and it also supports up to 32 SSDs. So I'm going to show you some of the performance numbers, and we do have white papers. We published a PCIe Gen 5 white paper, and one of the things that I think is interesting in that paper, if you have a chance to go look at it, the first thing we did was set up an environment where we baselined RAID 0 on X number of drives, and that's the baseline being, this is the theoretical performance of these drives. And then what we did is we did identical testing using a traditional hardware-based RAID controller, identical testing using SupremeRAID, and then identical testing using our technology. And what it really shows is the bottlenecks, and it also shows how we're able to overcome those and provide, once again, 100% of the read performance of the drives and up to 85% of the write performance of the drives for RAID. The testing that we did, it was a Gen 5 server, AMD. We had, in this case, it was 24 Kioxia 3.84 terabyte CM7R drives. So these are really, really fast PCIe Gen 5 drives. And we actually set up everything with maximum performance based on drive group with 24 physical drives. And so all of this is out there, and we used Ubuntu, and then we ran a number of tests, FIO, and we've got an entire test suite recommendation as well on our website if you want to kind of perform some of these tests yourself. But the net effect of this, on the top number, you can see we were able to achieve 28 million IOPS and 2 million IOPS on write. And this, comparing this to the other environments, from a performance perspective, on the read side, 260 gigabytes a second read. So we're achieving very close to 100% of the read performance of these 24 Gen 5 drives. And 100 gig to 110 gigabytes a second is right at 85% of the theoretical write performance of those drives. And so we're able to not accelerate the NVMe that you've purchased. What we're able to do is give you the performance that NVMe represents, because we get out of the way. Another key thing that we don't want to discount that's very important is understanding that the reason we do RAID protection is to protect data. And if you have a drive fail, the amount of time that it takes to rebuild a drive, especially when we're getting bigger and bigger drives, 15, 30, and 60 terabytes, becomes a critical problem, because if it takes days or even a week to rebuild a failed drive, you're now vulnerable to more failures. You're also running potentially in a degraded state. Because we do all of that rebuilding on this GPU using our peer-to-peer DMA, your CPU is not involved in the process. It doesn't take your CPU up to super high utilization. And because it's much faster than these older ASIC-based technologies, it's able to rebuild drives 5 times faster and even 50 times faster. The situation here is these technologies are still very useful because there's a lot of hard drives out there, and that's really where you still want to use the traditional RAID cards, because they have caching and other things on them that help you improve the performance of hard drives. They just simply can't keep up in this kind of an environment here. So, the rebuilds, as I mentioned, are very, very important. And I did mention caching. We do not do any caching, so there's nothing persistent on our cards. It's a straight pass-through. Actually, caching in our case would introduce latency into the data path. So we're a straight write to the SSD and then acknowledge MAC to the application. And then this just compares the performance numbers of all 3 cards, depending on what your environments are and what your needs are. You can see that, they're all extremely powerful. And still, even the smallest card can outperform the traditional cards on the market. From a compatibility perspective, we have done an extensive amount of work to make sure that we work with a large number of operating systems, and we're constantly testing new kernels and adding more kernels. We also have Windows support. We have tested a huge number of the SSDs on the market. We partner with almost all of these companies as well. This does not mean that we don't support an SSD. If you have one that you want us to test, we're happy to do so. So this is almost all of this is customer driven. We have also tested with ARM as well as AMD and Intel, and we have interesting numbers on all of those. We even have an ARM server at our headquarters. In terms of virtualization, we do a lot with the KVM-based hypervisors on Linux, like Proxmox, KVM, etc. We work with Hyper-V. We are next year going to be releasing more extensive support for VMware, but today we do support Workstation Pro. So I think now we want to get to what matters to everybody here, which is how can this potentially help me in HPC? You might have thought of some ideas yourself as I went through that. But what we're going to do here is talk about a couple of different environments that we've been working, companies and environments that we've been working with. If you've never heard of OS Nexus, they have a product called QuantaStore, and it's actually a framework that allows you to build large Ceph clusters. And we have been certified, and they've actually integrated with us. Their UI actually integrates to our technology, so you can actually use their UI to define RAID groups and things like that. But essentially, what they're going after is being able to improve the performance of Ceph as well as improve its resiliency. One of the issues with Ceph is when you use the erasure coding across large clusters, it spreads out all the blocks across all of the drives and nodes in a cluster. And so if a single drive failed in one of these clusters, what can happen is basically all of these drives and nodes have to light up in order to send the data back to rebuild that failed drive. That can result in degraded performance at the node level and also heavy network traffic. There are parameters on Ceph that you can use to throttle that so it doesn't impact you as much. But when you throttle it like that, your rebuild times will become very extended. So what OS Nexus has done is integrate us, and they're helping customers where they have a vulnerability and need to minimize the local rebuild time and also deliver this ultra high performance. We've also been messing around with ZRAID or RAID-Z on ZFS, and we can actually accelerate ZFS. A lot of folks love ZFS. It has a lot of really great data protection and resiliency features. The way we would actually support that is we could create a RAID volume, provide it to RAID-Z. RAID-Z would see that as just a RAID 0 volume or disk, and then continue processing. So ZFS would be able to work fine with this. We haven't published anything on this yet. We're about to, so stay tuned if you're interested in that. One of the other areas that we've been messing around with is parallel file systems, and so most of the work that we've done in this area revolves around BGFS. And in fact, Philip Falk and the BGFS folks unfortunately are in an offsite meeting somewhere in East Asia, and they were unable to attend today. But we do have a partnership with them. We've published white papers, and all those kinds of things. But essentially, what started this whole process with us in BGFS was a Dell HPC solution architect, who I'm going to call out, my buddy Fabrizio Bronzati, who works for Dell, and he is down in Brazil. And I ran into him at SC22 in Dallas. And when we started talking, he asked me about this because I used to work at another company where I had partnered with him. So he asked me what Graid technology did. And when I explained it to him, he said, wow, we've got this problem where we have some customers who have really, really large NVMe scratch space, but they cannot run RAID 0. They have to have drive protection, because if a drive fails and brings scratch down, they're going to have really, really long restart times. And if you're 3 weeks into a job, you don't want to have to go all the way back to the beginning, of course. And he said the problem is the only way to really protect it would be something like SupremeRAID 10, but that was costing too much money because now they have to buy twice as much storage as they actually need because of the RAID 10 overhead. So basically, you only get 50% usable capacity. So this problem was that it was effectively reducing the usable capacity. So he saw that an idea was, what if we did RAID 5 or 6 to protect scratch, and we can increase the usable space by 50 to 80% versus RAID 10, and yet maintain very close to the RAID 0 performance levels that everybody in HPC likes to have. So that's what we set out to test and prove. And it took us about a year, and we got there. We also can protect all the storage at the node level. So that there are a number of different areas that we can do this. And by the way, we are also doing some luster testing with Dell over in the Netherlands with some of the HPC environments over there. At this point, what I want to do is actually introduce Guy Laporte, and I'm going to mute myself for a little bit here and let him talk about his environment and the lab he has, and also their capabilities, as well as the cluster he set up with Graid technology. Guy?
Yeah, so hello everyone. My name is Guy Laporte. I work in the Dell Customer Solutions Center, and part of a pre-sales organization that is worldwide. Kelly, would you please advance the slide? Right, so we have offices around the world, and we provide various services for our account teams, and it's really with the goal of allowing our customers to take the best possible decisions when they purchase Dell solutions. If you can see, next slide, please, Kelly. We provide various services like technical briefings, design workshops, and in my case, most importantly, I run a lab dedicated to performing proof of concepts, and especially in the HPC and AI fields. So customers work with our account teams to define requirements as far as what they would like to evaluate. And we build these environments, and we either, we can run tests for customers, provide results, or we can allow customers remote access so they can actually test with their own applications, and then see how our solutions perform. Now, another thing that I really like to do is explore new technologies, and I had like a fair amount of experience on BGFS, and when I was we had this requirement to evaluate a solution that would provide resiliency with flash drives. We worked with Kelly's team to actually design a small system so we could run some tests and provide some results to an account team. And this is basically the system that I built and how it was tested. And it's actually pretty simple. It's just based on two R7525 servers. So for people who are not familiar with Dell servers, so that's our 15th generation Milan-based processors, 2U servers. This particular flavor of server had 64 core processors, the 7713s, and 16 NVMe drives. These drives are split into 2 NVMe backplanes, and they're connected directly to the PCI bus. And in order to provide resiliency in the server, we, like Kelly explained earlier, we leverage two of those Graid SR1010 cards, and in this case, each card is responsible for 8 NVMe drives. And what we did, we took 2 drives in a RAID 1 set to do metadata target, and we built a RAID 5 with the rest of the drives. for OSS. And we, in order to also maximize the network efficiency, we use two InfiniBand HDR 200 cards. So the way that we define services in BGFS so that everything, the performance is optimized as far as affinity. So we have one card, one IB card, and one Graid card, and one set of drives on one CPU, and the same thing on the other one. So both servers were identical. So at the end, we had 4 metadata targets and 4 storage targets. As far as how we tested, we had a set of 8 R6525 servers. So these are also Milan-based processors, and they were also connected to InfiniBand, and we ran some IO zone tests. All right. So as part of the testing, we also did a few, destructive tests like removing drives, and also we disable one of the Graid cards at the PCI level and verified that the other card took over the rest of the drives. Next slide, please, Kelly. So these are the specs, right? And I talk about it a little bit. The 7713 processors, we had just 256 gig of memory and 16 of 3.2 terabyte mixed use NVMe's, 2 of the Graid SR1010s, and ConnectX-6, 2 cards per server. And we had 1 on the client, and that was done with Red Hat 8.6. Okay. Next slide, please. All right, so this is a quick snapshot of the performance that was achieved. So you can see how it scales with the number of threads. So we tested from 8 to 512 threads. We obtained close to 80 gig of read bandwidth and 42 on the writes. So we were very close to the maximum network bandwidth that you can get out of the servers, and on the writes, we are also very close to the baseline of if we wrote directly to the disks as opposed to BGFS. Another test that we've performed, if you can go to the next slide, please, Kelly, is we implemented the body mirroring. So that is a function of BGFS that would allow, resiliency at the host level. So you can see that we got pretty much the same read levels. And of course, because you have to do mirroring, it split the write performance pretty much in half. So, so this is a snapshot of the tuning that was done to achieve these numbers. So Kelly and team is going to be producing a paper that's going to be available for somebody to do this, repeat this kind of testing. Now, again, going back to our capabilities, right, in the solution center, that's the one of the kinds of proof of concept that we often build for customers. In this case, these nodes have been put as permanent backend storage for our HPC cluster in the solution center. So we use it every day for various purposes. So that's it for me on that side. I think I'll pass it back to Kelly.
Very excited to be a permanent part of the Solution Center, and hopefully we'll have some people want to take advantage of testing with this to see how it works for them. So we're getting close to about 20 minutes left. I'm going to wrap this up a little bit here because I'm going to leave room for Q&A. So I think one thing that's worth pointing out is that we're a software company. So we're using off-the-shelf GPUs. We don't physically change them. We're shipping those 3 GPUs in the market that I mentioned, although we have tested unique situations for some of our partners. For example, we've been able to run SupremeRAID on an A100 MIG instance, so we know that it works. We have been able to run on A2 cards, A30, A40. So really, we don't get a whole lot more performance out of those because we're already getting 100% of the performance of the drives with those smaller cards. So the cool thing is, because we're a software company, a lot of the features in the future that we will develop and deliver will come with software upgrades. So, you know, additional operating systems. We're looking at even things like compression and encryption. We're working on some boot drive protection utilities. We will be increasing drive support from 32 to a larger number, probably 64. We will be developing and releasing our APIs and a management user interface. All of that capability will be upgradable for our customers because the underlying hardware doesn't have to change. We're setting world record performance. We free your CPU up. It's highly scalable, very easy to install, and it's very easy to use. So, you know, we appreciate the time that you've spent with us today. This kind of ends the slides. I could go up into the company things, you know, who we are, where we are, and all that kind of stuff, but I want this to be focused on the technology, and I will save this and send this to Carl because they'll probably make it available as a downloadable presentation.
Yeah, thank you, Kelly. Yes, we will definitely make these slides available. The recording today and the slides will be available in the community portal. So Guy, I'll turn it over to you. We have a few questions that are in the system, and I'll let you either kind of take lead in answering them or positioning them to Kelly and team.
Sure. So I look like a lot of them have been answered so far. One of the question is if we had any benchmarks done with MPI-IO. I believe that we have just tested with IO 500 and, you know, FIO IO zone, but, you know, we can take that we can test with other benchmarks if there's a need to do. So that's something we could do. If we have tested with larger 30 terabyte NVMe drives, not at this point. This was more, you know, about a testing the functionality, right? And actually also meeting the expected performance level. We often partner with, you know, our suppliers for drives like NVMe drives. So, for example, we get drives from Kioxia or Micron or other suppliers. So for a specific proof of concept, that's something we can do.
Hey, Guy?
Yes.
I would chime in that we actually have tested some of the QLC drives like Solidigm's 30 and 61 terabyte drives. And there's a white paper that we published with, I believe, Storage Review. So that's out there if you want to see it. Obviously, those are read intensive drives. They're not meant to be written to as much, but we got really good performance with those.
Very good. All right. So there's a question, Kelly, about GPFS. So do you have any plans to test with GPFS?
I'm going to let Bill or Leander answer that. I know that theoretically we could, but I don't know if we have a plan yet.
Yeah, I have yet to see it. I don't know if Leander has any visibility into that. not so far, but we are very welcome if some of the partner want to work with us for the testing.
Okay. So the next question is about NVMe over Fabric. So can you talk a little bit more about how NVMe over Fabric fits? Can it be used to compose RAID volumes with disk from other hosts? For context, we're running Accelero under GPFS, and we're looking for an Accelero replacement.
Absolutely. So we do support NVMe over Fabric, and we can actually act as an initiator or as a target. And so just one little slide here that kind of shows what we do in a target offload capability. If you have our environment installed in a server like this, we can take these volumes that we've created, virtual disks that were, stored on these actual devices, and we can make them available across Rocky or TCP for NVMe over Fabric, so that would appear as a local volume in these remote hosts. On the other side, if you have a JBOF, so we do work with some companies that make JBOFs, including Dell. Dell has a TCP-based JBOF, which is basically just a bunch of flash. So they have an enclosure that they could actually use their target offload to make those physical drives appear in a remote host. We can put one of our cards in that remote host and actually then provide the RAID for those disks, at that local level.
Right. So one more question is about how do your system compare with other software-defined storage solution like Weka and VAST? So, I mean, the Graid is really the layer underneath, right? So we tested with BGFS. So the real comparison would be BGFS versus Weka or VAST. If you could leverage Graid virtual disks to implement those solutions, but that's where the comparison has to be, right, at the file system and not on the layer underneath. I don't know if Kelly or Bill wants to add to this.
Yeah, I mean, I think you hit the nail right on the head there, Guy. It's really presenting the block storage and protection against drive failure. What you do with the layers above that is up to you. So it could be integrated, but it doesn't necessarily compare.
Yeah. All right.
We've had discussions with Weka.io. They have their own erasure coding technology, and so they're not really that interested in what we have to offer. Since BGFS doesn't have that technology, we actually, provide a value to those environments. And I believe the same could apply to, Lustre. We have found that in erasure coding environments like Ceph, we have a value add there, as I mentioned, in terms of, impact of rebuild performance and things like that on large, especially large clusters where, when you lose a drive in Ceph, it'll go to a stunned state for a while, and then it starts, lighting everything up, and your network goes to its knees for a rebuild, and we can help solve that problem.
All right. One more question. How can we test your product in our lab? We have all the devices you showed in the presentation.
So if you can give us a call, if you have an actual T1000 or T400 or A2000, we can actually provide software for you to test, a POC license to test on that. We also have lab pricing for cards if anybody wants to buy an actual bundled card with the software that comes with it.
All right. The next question is, did I miss what happens when one of the nodes needs to be rebooted? You mentioned disabling one of the cards. Right. So, I mean, it's all about how the file system can handle, losing a host, right? So it's all about how, in this case, BGFS would handle it. As far as the Graid level, if you lose a host, and you have to design your solution to be able to handle that. at the component level, that's where the two cards come in, and one card can back up the other one if there's a failure of a card.
I think, Guy, to simulate a card failure, you disabled one to prove that the failover would work, which is what you did, because that's the only way to test that, is to simulate a failure by disabling. So a reboot did not have to happen. You will have to bring this server down to replace a failed card, however, at some point.
Okay. One more question. We are looking for an Acceleroid replacement for this application. Our space needs are modest, about 100 terabyte, but read speeds are important. How many SSDs would be needed to get max performance on HDR 200 or NDR 400 fabric?
Mileage varies depending on the SSD that's being used. The specs that we put out are based on 24 Kyosha drives. I believe it's the CM7, Kelly.
Yes. And I think our read performance inside of a single server at 260 gig a second would be way more than you would be able to push through an InfiniBand network, correct?
Yeah.
So you could back that down to 8 drives or 10 drives or whatever. So in the BGFS testing in Guy's lab, I think that what we showed is that he had 16 drives per node. And we were able to basically, the bottleneck here now is this network, and they had 4 200 gig NICs. So that's 800 gig of gigabits a second. And, you know, we could add more drives into these nodes, and we're still going to be limited right here because we've now hit the maximum bandwidth. So the only way to get more performance out of these nodes at this point would be to add more NICs or increase the speed of those NICs to 400 gig. So it's it's the typical, when you put something really fast in a server, you almost always just expose the next bottleneck, right?
Okay, so yeah, next question. From system design perspective, do you prefer low core count, high frequency CPU, or high core count? I'm sorry, low core count, high frequency CPU, or high core count, low frequency CPU for Graid storage system? I'm gonna let maybe Bill talk about this, but basically, your CPU concern will be more about, you know, your file system, like what the best practice would be for BGFS in the case of BGFS. I don't think it really matters much on the Graid side, but Bill, I'll let you complete that answer.
Yeah, I think you actually hit it right on, Guy. We have seen both situations where we've been able to drive the right performance out of those drives. We do have minimum requirements, which can be found on our website as well, but that would be minimum requirements and something that we rarely see because the systems that people are purchasing for high-speed NVMe are certainly a lot beefier than what the minimum would be. So it really depends on your application.
Yeah, Bill, I would chime in there. If you're going to build a storage server that's just serving data up with NVMe over Fabric or providing storage space for a parallel file system, it's probably not necessary to have such a powerful CPU. However, if that's going to be a single standalone node and you're going to be running, you know, a high performance, you know, in-memory compute database like Redis, you might want to have a lot of CPU in that box to be able to handle the application.
All right. Another question. What's the impact on device wear? RAID is going to incur some write amplification. Are small random writes a problem? And related, do you do anything to imbalance the wear across the managed devices so they don't all fail at the same time?
Yeah, I'll ask Leander to comment on that. Just my real brief observation after 2.5 years of runtime here is that we have yet to encounter that as an issue. I know it's been brought up in question, but in reality, we have yet to see it.
Yes, I think Bill is right. So I don't have further comment.
Okay. And I think one last question. I don't understand how the encoding can work without seeing all the data. Can you explain? I.e., since not all the data goes into the GPU.
Yes, and give me 1 second here. I have 2 slides at the end that I have here just in case that question came up.
Yeah, and that actually did come up earlier when you were presenting, Kelly, because they were saying that this must present a bottleneck because the data has to flow through the CPU. But one of the things that I responded with is that we're implementing a kernel module, and we're able to read some of the data directly from the CPU, which would lead somebody to believe that maybe that increases CPU utilization, but it actually decreases that because of the proximity to the cache. If you want to walk through that, Kelly, that's fine.
Yeah, so on the read side, if this is a SupremeRAID managed volume right here, your application issues a virtual disk read command. That fetch comes down to our driver. We redirect that to the SSD and then reissue that command, and then the data goes straight from the SSD to the application. So the data does not get read through our card back, it goes straight to the application. So that's how we're achieving that 100% performance on read, because we're just acting as a traffic cop at this point. On the right side is a little more complex, because on the right side, data does have to come to our card for us to do the parity calculations. And so what happens here when an application writes the data, it goes into a user buffer. The data itself then gets laid down. At the same time, our little kernel module here, which is doing what we call intelligent parity reduction, sends a reduced user data set to our parity buffer. We read the old parity in, and then we write the new parity. So this is the piece where on the theoretical write performance at RAID 0, we get about a 15% penalty, but still compared to any other solution out there, it's a massive difference. So this hopefully explains how we're doing some of our magic. These are the patented, really super secret sauce things that we have that make this work. I think we're pretty close to time here, by the way. So
yeah, we're about there. We have maybe a minute left. Guy, I don't know if were any last comments or questions you wanted to address, or if we
I think we covered them all.
Okay, perfect. Well, Kelly, Bill, appreciate you guys at the Graid Technology team. I know Guy has been a valuable instrument in working with you guys, and we appreciate him and his participation today, representing the Dell Technologies team. And thank you, everybody who's attended today, and we look forward to seeing you next week. So have a great day today, everyone. Thank you.